like I said, I have ambitious goals. I think I'm going to be taken down a peg, but that's okay. I'm going to speak about some optimization. I genuinely can't remember if it was someone in this class or the other class that asked about optimization. Ooh. So I am going to do some optimization examples. Personally, I'm not saying don't waste your time on it. That's not what I'm saying. But if you go to past papers and you look at the optimization question, it is between 5 and 8 marks. So if we compare that to how many marks your calculus is actually worth in the paper, 5 to 8 marks of 35 marks is really not significant. Okay, I would much rather you are getting the 27 to 30 marks of first principles, derivatives, cubic functions, derivative graphs, etc., and so be it we lose out on 5 to 8 marks with optimization, then you're getting 5 to 8 marks on optimization and losing out on 27 to 30 marks of the stuff that we should know. So I'm not saying it's not important. And I think if you can do optimization, it really does just boost your problem solving and complex thought processes, which is why I'm going to do some examples. But realistically, grade 12s, if you know that calculus is already something that you're not super comfortable with, you leave the optimization question, you can come back to it at the end. Like I say, it's never going to be worth more than 5 to 8 marks. If it is, that's mean. But even then, even if it was worth 10 marks, that is still not the majority of the calculus marks. And so you focus on the other stuff. All right, but because it was asked, I am going to do some questions. We'll see how we go. I would like to revise some general calculus, but we'll see how we go. We have the boot camps to revise more if we need to. Let's rather kind of see what optimization is about. All right, so optimization in calculus is real life applications of calculus. What it allows us to do is it allows us to take real world scenarios and essentially use maths to solve problems. The problems that we're going to be solving when it comes to optimization is things like, I don't know, let's say, for example, you own like a baking business or a packaging business or something like that, and you needed to produce the packaging or you needed to produce boxes or whatever the case is, but you wanted to do so that you used a minimal amount of materials, optimization could come in. If you can come up with a formula, which we can, and you'll see Nana, that describes the amount of packaging you would need to create a box, you can figure out what dimensions your box should be in order to use the minimum amount of materials to create that box. We can work out dimensions of 3D objects that would create a maximum volume that it could contain. We can, I suppose if you think of it in terms of like business accounting, if you came up with an equation that described your profits, taking into account selling prices, cost prices, variable expenses, all of that sort of stuff, we could use calculus to maximize our profits. We can use calculus, those of you that do physics, I don't know how many of you do physics, things like velocity, acceleration, rate of change, all of that can be calculated using calculus and optimization. So optimization is real world applications of calculus. And what I am going to say is that the method is not hard. The method is nothing different to what we've been doing. It's finding the derivative, making it equal to 0, solving. What is tricky is taking the information that you've been given, analyzing it appropriately, and understanding how to use that information in order to get to where you need to be. So these sorts of questions would be considered complex or problem solving because there's not necessarily always a clear starting point. We kind of need to analyze our information very carefully to know where to begin. Right, I will do my best to give you some sort of like tips of where to start and what sort of things you should be using in certain instances. But in reality, it really does come down to, have you read your question carefully? Do you know what information that you have in order to use to answer your questions? Okay, I have obviously in all of my, spiel, left out some information for this first question. So I'm just going to chuck it in. Cylindrical can. I've left off the volume, and I thought I put it in, but I did not. Okay, next little tidbit of information I'm going to give is that optimization is very much reliant on your knowledge of your measurement formulas. So measurement formulas, surface area, volume, area. We expect you to know the basic shape. So I expect you to know how to work out the area of a circle, square, rectangle, triangle. I expect you to know how to work out the volume of right prisms. Right prisms are one where the base shape and the top shape are the same. So like a cylinder, it's got a circle on the bottom and an identical circle on the top. That's a right prism. A cube, a square on the bottom, the identical square on the top, right prism. So we expect you to know those. I will talk about that a little bit more in a second. We generally give you formulas for shapes like spheres, cones, and pyramids. I'm trying to think of any other shapes that I've forgotten. Spheres, cones, and pyramids. However, when we give you those formulas, I'm not going to say the volume of a sphere is. I'm just going to say V equals, and I think it's like 4 pi r cubed or something like that. I don't even remember it. So what that means is even though we give you the formulas, you still need to be able to look at it and say, okay, cool, I know that's the volume of a sphere, or I know that's the surface area of a cone, or whatever the case is. So you kind of have to know them. It just is nice that we give them to you and you can kind of think, oh, I kind of remember that. I used it in a question with a sphere, so that's a sphere. What I will do for you guys is I will put together a whole like summary of all the formulas that we use in measurement, and I'll put that on Google Classroom for you just so that you have it. And I'll make a little note of which ones we expect you to learn off by heart and which ones we do give you, but you should still be able to recognize. Okay, because this section very, very much dependent on measurement. And unfortunately, many schools actually leave out measurements sometimes as early as grade 10. I mean, I'm trying to think. I'm not even sure if I teach measurement in grade 9 anymore. So it sucks because we're like, oh, here's measurements. Don't talk about it for 4 years. Oh, here's measurements again, using calculus. Not an ideal situation. I'm fully aware of that fact, but just something for you to bear in mind. Okay, so I will put those formulas up for you so that you can see them, work with them, get familiar with them. Alrighty, so excuse me. We have a sketch of a cylindrical can with a volume of 340 milliliters, sorry, is shown alongside. We've got two questions. We want to calculate or determine the height of the can in terms of R. So basically that means H equals an expression that has R in it. And then we have been asked to calculate the length of the radius of the can if the surface area is to be a minimum. So packaging. I want to spend, or I want to use the least amount of material to make this can that will still hold 340 milliliters. How wide should the can be, essentially, in order to create that minimum amount of packaging? And that's where the differentiation or the calculus will come in. All right, before we get into that, just a couple little things in terms of measurement. So we work with either 2D shapes or 3D shapes. You're going to see as we start to go through this that you are often going to have to set up two different equations or use two different formulas in order to answer your question. So for 2D shapes, these are flat shapes. The formulas that you would work with have to do with the perimeter of the shape and then the area of the shape. Those are really the only two measurement calculations that we can do when it comes to 2D shapes. When it comes to 3D shapes, it is surface area and volume. Those are the two measurement calculations we can do. Now, often what is going to happen is I'm going to give you a piece of information. So like over here, I have said to you the volume of the can. I've given you volume. And so when you start with these questions, and this is my like little tidbits, hopefully it's helpful. When you start with these questions, start with the information you've been given. So question A says determine the height of the can in terms of R. Awesome. How must I do that if I don't know the surface area, if I don't know the volume? But I have the volume. So I'm going to start by using my volume formula for a cylinder, and I can hopefully manipulate that to find the height. So always start with what you know, and you move from there. So question A, like I say, we're finding the height. Does anyone know what the volume of a cylinder is? I understand that I'm putting you on the spot and you probably haven't done this for years, but I'm going to ask anyways. Oh, okay. Like I said, I will send them all to you. Don't stress. Don't even stress. Honestly, I've just been doing this for so many years, it's like etched in my brain. But I can tell you right now, I could not give you a formula for a pyramid, a sphere, or a cone. No idea. Right. This is a right prism. So again, it's it's a 3D shape where the shape on the bottom is the same as the shape on the top. Any right prism. So a cylinder, a cube, a rectangular prism, or triangular prism. Triangular prism, this is not going to be a beautiful triangular prism, so just roll with me. Would be something like that, like a Toblerone box. That's a triangular prism because it's got a triangle on the bottom, triangle on the top. Any right prism. To work out the volume, you take the area of the base shape and you times it by the height. So in this case, my base shape is a circle. So the area is pi r squared. We're going to get there very slowly. Pi r squared. And then we will times it by the height of my cylinder. So pi r squared times height. So any right prism is area base times height. Right, now remember, we've been given the volume. However, what we need to bear in mind is that the volume has been given to me in milliliters. I'm looking for lengths. I'm looking for dimensions, which means I need centimeters or millimeters or meters or whatever. Now, a conversion from millimeters to centimeters is incredibly easy because it's a one-to-one conversion. 1 millimeter is 1 centimeter cubed. And so what that means is 340 milliliters, I don't know why I keep saying millimeters, is 340 centimeters cubed. Very easy conversion to remember, one-to-one. And so what that means is now in my formula, I can substitute in a value for my volume. 340 is equal to pi r squared times height. Okay, now remember the question said, determine the height of the can in terms of r. So we want height in terms of r. If you now look at my equation, the only two unknowns I have are r and h, height and radius. Great. I'm wanting to isolate my height, so I'm wanting to solve for the height, determine height. And so what that means is that I'm going to have to divide both sides by the pi r squared. So in order for me to isolate height, I will have to divide by pi r squared on the left and the right, because that gets rid of it on the right. And so what I found is that my height is equal to 340 over pi r squared. So not the nicest looking expression by any stretch of the imagination, but I have determined the height in terms of r. So we've answered question 1, question A, whatever we're going to call it. Now that I have that, I can move on to my next question. So remember I said we're probably going to use surface area and volume for 3D shapes. We've used the volume. The next question says, calculate the length of the radius of the can if the surface area is to be a minimum. Now I can move to the surface area formula. A little trickier, but we'll chat about it now. In these questions, we will often say where the surface area is to be a minimum or where the area is to be a maximum or the distance is to be a minimum or maximum. But if you see that word minimum or maximum, you need to remember what we have already spoken about because we have already dealt with this idea of minimum, maximum. We have dealt with this when we spoke about our cubic functions. In our cubic functions, we spoke about the fact that your minimum or your maxima are your turning points of a graph. And so what that means is we are looking for where our first derivative is equal to 0. That is how we find turning points on a function. First derivative equals 0, and we get the x coordinates. This is what we want to do here. We want to essentially take a formula or an expression for the surface area, find its derivative, and then go and work out what the r value would be at that minimum surface area or at that minimum expression. So anytime you see a minimum or maximum situation, you need to think, okay, cool, first derivative equals 0, and I can solve from there. So this is what we now need to think about as we head into the second question. Firstly, I'm working with surface area, so I need the formula or an equation to express my surface area. Now, guys, surface area is quite literally just the area of all your surfaces. So if you think of a cylinder, you have your two circular surfaces. This is not a beautiful net, but it's okay. And the rectangle in the middle. Now, if you imagine, it's not going to be great, but if you imagine a cylinder, just excuse this. Right? It's not my best demonstration I've ever done in the whole world. There's your cylinder, right? Cylinder. Cylinder. Lovely, lovely, lovely cylinder. What I need you to see is that the circumference of the circle, when you flatten it out, becomes a length on your rectangle, right? And so when we are determining the surface area of a cylinder, it is as follows. You have two circles, top and bottom. So two circles would be 2 pi r squared, because the area of one circle is pi r squared, so times 2, plus the area of that rectangle in the middle. Now, the rectangle's dimensions are the height, how tall the cylinder is, but this length of your rectangle is the circumference of the circle. So this length is 2 pi r. So you will have plus 2 pi r times h, length times breadth. This gives us the surface area of our cylinder. Again, I'll send you these formulas. I've just done this too many times in my life and have this useless information stored in my brain and then forget other important stuff. All right, so now we've got our surface area. The next thing we just need to take note of is the fact that I have already solved for h. So here, h is 340 over pi r squared. That means that in this formula, I can replace that h with my expression. Now, the reason I want to do that is because I've been asked to solve for the radius. I don't want an expression that contains h. I want an expression that only has the radius, which is what I can now do. So my surface area is equal to the 2 pi r squared plus 2 pi r times my height of 340 over pi r. Like I said, we want to figure out where the surface area is a minimum, so we are going to have to find the derivative. But remember, in order to find the derivative, you have to simplify. So we're going to simplify the situation. This first term is fine. The second term I need to multiply. Someone bit me on the head. Lovely. Right, if we simplify, the pi and the pi cancel. The r, and it would help if I wrote r squared. R squared in my denominator. 1r cancels with 1r in my denominator, and I'm left with 2 times 340 over r. 2 times 340, sorry, is 680. So 680 over r. And remember, we don't like variables in our denominator. And so that means we're going to have to write this as 2 pi r squared plus 680 r to the negative 1. This is now the format that I want in order to find my derivative. And so now I can find the derivative of my surface area in terms of r. Remember, notation is very important. So you will start by saying what you're finding the derivative of. Surface area, use your prime or your apostrophe to indicate it is the derivative. And then in brackets, you refer to which variable you're working with. In this case, radius. Remember, pi is not a variable. It's just a symbol we use to represent a number. So now we find the derivative. Don't know why my brain had a bit of a brain fart there, but we're just going to move on from that. Take your exponent, multiply by the coefficient. So 4 pi r, subtract 1 from your exponent, minus 680 r to the negative 2. So that is my derivative expression. Minimum, so where your derivative is equal to 0. And now we solve for r. Now, guys, from this point, you don't need the negative exponent. So put it back into its positive form. So 680 over r squared is equal to 4 pi r. And you can solve for r much easier. I've obviously run out of space, so let's carry on up here. Times both sides by r squared gives you 680 equals 4 pi r cubed. We want to get rid of that 4 pi, so we're going to divide both sides by 4 pi, which means that r cubed is equal to 680 divided by 4 is 170 over pi. And to get rid of the cubed, we cube root. So r is equal to the cube root of 170 over pi, which is 3,78 centimeters. So what we have discovered, or what we have determined here, is that for my surface area of this can to be a minimum, so to use the smallest amount of packaging to still contain 340 milliliters, the radius of this can needs to be 3,78 centimeters. If I can produce a can that has a radius of 3,78 centimeters, I will be using the least amount of packaging to still contain 340 milliliters. And this is why calculus in the real world can be very useful. If you were producing metal, yes, metal, don't know why I panicked about what a can is made out of. If you were producing the metal, the tin or whatever, aluminium, whatever it is, for canned drinks, you can maximize your production by minimizing the amount of material you are using to produce that packaging. And that's essentially what we've just discovered here. All right, so let's take a screenshot. And I was just about to say if we have any questions. So Lorato?
Ma'am, when we are rooting the 170 over pi, do we have to include the plus or minus in the beginning, or we can just leave it out since it's supposed to be a positive value?
So you have raised a very important point in that this is a cube root because it's r cubed. So it should actually say cube root. Thank you. However, if it was a square root or any sort of even root, then yes, we do need to have plus or minus in front of it. You could then eliminate the negative because, like you say, it's a length, so it has to be positive. But yes, if it's a square, fourth root, sixth root, etc., you will have to put the plus or minus there. I think I do have an example like that coming up. So we'll have the plus or minus, but then, like you say, we can disregard the negative because it's not applicable in the situation.
Okay, thank you, ma'am.
Okay. Yes, sorry guys, cube roots, because to get rid of a cube, you cube root, not square roots. Excuse me. Right, any other questions? Obviously, just ask if you have, like, just pop your hand up, put it in the chat. I'm here. But I do understand that this isn't necessarily always the most straightforward, clear thing, so rather ask. Okay. Right, so we're going to have a look at this one. This was from last year's finals. So this is what the matrics of last year got as their question 9. I think this is the last question of calculus before probability. Optimization questions are the last question of calculus. Your first question starts with first principles, derivatives, sometimes tangents to a curve. The next question deals with cubic functions, all of that fun stuff. And then your next question is optimization. Right. I hope that me talking makes you see how important past papers are. I can tell you literally, without looking at a past paper, exactly what questions you're going to be asked. Question 1, you're going to get this. Question 2, you're going to get this. And this is just because it's the same people sending the papers over and over. There's not a lot of deviation. Unless they're feeling particularly inventive and creative one year, you're not going to get too much deviation from what you see in past papers. This is why we always recommend them. Right, now that my little tangent is over, let's have a look. So this is what they got last year. The diagram below represents a printed poster. Rectangle ABCD is the part on which the text is printed. The shaded area ABCD is 432 centimeters squared, so the actual area, and AD equals X. ABCD is 4 centimeters from the left and the right, and 3 centimeters from the top and the bottom. So we've got a sort of edge around the printed area that has those dimensions. First question is show that the total area of the page is given by A of X is equal to 3,456 over X plus 6X plus 480, and then determine the value of X such a total area of the page is a minimum. We're going to ignore those questions for now. And all we're going to do is quickly look at our diagram and analyze the information we've been given, just so that we do know what we're working with. And again, if you've sort of taken note of how I deal with questions in lessons and not only in calculus, this is exactly how you should be doing it. Don't yet look at those sub questions. Take the information that you have, look at the diagram or the graph or the geometric construction, whatever it is, and just make sure that you fully are aware of everything you have at your disposal. So everything that you have to use to answer your questions. Alrighty, so first things first is we were told that the shaded area is 432 centimeters squared. So this area in the middle here, can't see a single thing. Well done. Ay, ay, ay. Right, so there's the area in the middle here. This is the 432 centimeters squared. Does anyone remember how we determine the area of a rectangle? What is the formula for the area of a rectangle?
Ma'am, is it 2LB?
Okay, so careful, sorry, my brain took a little second there. 2LB would be perimeter. 2 length times plus 2 breadth would be perimeter. You're on the right track though. If we just drop that 2, it's just length times breadth.
Oh,
Okay, so 432 centimeters squared, and exactly this is determined by saying length times breadth. Okay, not the best color I've ever chosen in the whole wide world, but you know, I'm all about making smart choices in life. Let's see if this is better. Yeah, that's a little better. We'll just pretend that's better. Okay, right, so length times breadth is how we work out the area of a rectangle. It's fine, we can see what's happening. Next thing that we were told is that AD is equal to X centimeters. Okay, so if we go to AD is just the side length of my rectangle, which means that it is going to relate directly to that length over there that we've just written down. That is X. Now, hopefully what you see is that we don't have the breadth. We do not know what the length of AB and BC are. So that's a bit of a problem. However, you've been given an area, you know that area is found by length times breadth, and you know the length, it's X. So we could actually go work out the breadth. The next thing that we were told was the edges around the rectangle. I'm not even going to make an attempt to highlight that stuff. You can see it labeled. But what it does mean is that if you were to go and have a look at the whole page's length, so what I mean by that is from end to end, for example, the length, you would have the X in the middle, because remember, this length is X, and then you'd have the extra, I don't know why I said 3, the extra 4 centimeters on either side. So that means in total, this length would be 4 plus X plus 4, which is X plus 8. Again, we don't know what the breadth is. We know there's 3 centimeters on the top and 3 centimeters on the bottom, but I don't know that middle section, so I'd have to work that out. Right, so we've already got a fair amount of information from just looking at the diagram. So the first question says, show that the total area of the page is given by that expression. Remember I say to you, whenever you get show that or prove that questions, pretend that you haven't been given that and just go and work out the area of the page. Now, area of the page is a rectangle. We know the length. We have just determined that that length would be X plus 8. However, we need to figure out the breadth. Before we can get to the breadth of the whole page, we first need to start with the breadth of the interior rectangle. Because once I have that, I just add 3 on both sides, and I've got the breadth of the entire page. And this is now where it goes back to what I said earlier. Start with the information you have been given. We were given the area of the small rectangle. So we were told that the area of ABCD is 432 centimeters squared. Okay, so we're going to start with that. We know that this is determined by saying length times breadth, and we know that the length is X. So X times B. We can go and figure out the breadth. Yes, it's in terms of X, but we can figure it out. If we divide both sides by X, the breadth is 432 over X. So up here, this breadth, so DC is 432 over x. That is what we have just determined. And what that now means is that in terms of the breadth of my entire rectangle, it would be the 432 in the middle over x plus 3 on either side. So plus 6. 3 at the top, 3 at the bottom. That is now the breadth of my entire rectangle. And so just by using what I initially was given, I was able to determine that bit of information for myself. Now this is helpful because I've now worked with the area of that interior rectangle, but I've been asked to find the area of the whole rectangle. So now I can use that information to set up an expression. So the area of the entire big rectangle would again be equal to length times breadth. We know that the length is that x plus 8 that we spoke about earlier. Excuse me. And the breadth is, as we've just worked out, the 432 over x plus 6. Remember, the plus 6 is because we've got 3 centimeters at the top, 3 centimeters at the bottom, and that must be added to my breadth. All right, so guys, again, I truly think that with these questions, the most complex part is just understanding what has been asked of you. Okay, once we've done a bit of analysis of the diagram, the information, it definitely makes life easier. You start with what you know. So we started with the area of the interior rectangle and you work your way out from there. Right, so now we've got an expression for the area and we now need to get our two brackets of x plus 8 times 432 over x plus 6 to look like the 3,456 over x plus 6x plus 480. That is what I need to get. I need to show that that's true. And there was a lot of that in that sentence, but anywho, this is where we now distribute. Again, this is not hard. You are foiling, you're distributing. But because the terms are not so nice, especially that 432 over x, just be careful. So the first multiplication that we're going to do is x times 432 over x. Those x's divide away, they cancel each other. So that is just a product of 432. Right. The next product, x times 6, that's easy enough, 6x. Don't know why it's being difficult, so we're just going to make do. Okay, so 6x. I didn't get any better, did it? Right, then we move on to multiplying that 8 into my bracket. There we go. So 8 times 432 over x. Unfortunately, nothing simplifies here, so I'm going to have to say 8 times 432 and then the 1 times the x. 8 times 432 is 3,456 over x, and 8 times 6 is 48. We have some like terms there, the 432 and the 48. So 3,456 over x plus 6x, 432 plus 48 is then 480. And hopefully what you can see is that this expression that we've just gotten is exactly the same as the expression we wanted to prove the area is. So now we have an expression for our area in terms of x. Right, again, not hard, just not very nice because of the numbers that we're working with. But if you remember your basics of multiplying fractions and working with fractions, it isn't tricky. If you need to do like a little separate bit of working out, that's what you do. Have your rough piece of paper with you and you can go from there. Right, any questions before I move on to 9.2? Okay. Lorato, sorry.
Ma'am, how much would a question like this count? Because I think in my June exam, I got a similar one.
I can tell you exactly what this counted. Let's not make my life hard. Let's just look at the paper. I want to say this was 2 or 3 marks, but I also could be talking absolute nonsense. So let me rather just double check. This was last year's paper. So this question that was 3 marks, and the next question is 3 marks. So your mark allocation, if you want to know that, would have been, and remember to show that question so you don't get an answer for that final expression, because we did actually give that to you. So your mark allocation here would be a mark for getting your B. So B is equal to 432 over X. A mark for getting the correct length, so adding the 4 on either side, and then a mark for the breadth. Thereafter, it's simplification and getting to your answer. So there's no marks allocated for that because I've given you the expression already. It's more marks allocated for you actually using the information that you've been given and getting the appropriate expressions to get that value or to get that answer. Right, so in this case, guys, last year, it was 6 marks on optimization. 6 out of 150 is 4%. Okay, which is very nice, but I would much rather we lose 4% and get the other whatever percentage that we're getting than, spend all our time on this. Alrighty, Roo. So we've got 9.1. Now we want to do 9.2. As long as there's no other questions, you can just interrupt me if there are. So 9.2 is asking us to determine the value of X such that the total area of the page is a minimum. Again, second you see maximum or minimum, you need to find the derivative. Now, grade 12, if you weren't able to get this area in question 9.1, it's fine. Yes, you lose 3 marks, but it's fine. You now use that expression in your next question because we want to find the minimum, so we have to find the first derivative of the area expression. So my area is equal to this whole situation. Remember, formatting is important, so I don't want that x in the denominator. So this would have to be 3, 4, 5, 6 x to the negative 1 plus 6x plus 480. And now we can find the derivative. So the derivative of the area in relation to x would be minus 3,456 x to the negative 2 plus 6. The x falls away, and obviously that constant falls away. We're minimizing, or we're finding the first derivative, so we make this equal to 0. And again, I would now write that with a positive exponent. So minus 3,456 over x squared plus 6. So 3,456 over x squared equals 6 times both sides by x squared. I can't write numbers in an order today. Divide both sides by 6 so that we get our x alone. 3,456 divided by 6 is 576. And this now goes back to Lorato's question earlier of if we now go in square root, which we have to get x alone, I will get a positive and a negative solution. So it's positive or negative 24. But because it's a length is never negative. Physics people, the negative would indicate a direction if you are moving in a direction, but the actual measurement of length, of distance, is never negative. So we would get x is equal to 24 centimeters. So again, that's saying that that middle rectangle's length must be 24 centimeters, in order for me to get a minimum area covered by the page. All right, excuse me. Again, if you can't get the expression, you just go ahead and use what you've been given, especially if it's show that it's given to you. You lose the 3 marks initially, but you can get the other 3 marks by finding the derivative. Sorry, it's always the derivative equal to 0, and then you solve for what you need to solve for. Now, this question said determine the value of x. You've solved for x, you're done. But if this question had said determine the minimum area of the page, you would then need to take this x value and substitute it back into your area formula. Okay, so if this had said determine the minimum area of this post or whatever. You would take this x and you would substitute it back into your original area equation. You've got the value for x that would create the minimum. You just now need to find the actual minimum area. So sometimes it is one that is asked. Generally, it is just the value of x, but just read your questions carefully again. Like I say, getting the information and understanding the information is really important for these questions. All right, so let's take a screenshot of that. If you've got any questions, you can ask. I'm going to do one more type of optimization question that can come up with relation to functions, just because it's actually something you've done before. It's just now we can use calculus. And then, like I say, we will do some revision of all the other calculus when we start revising for trial exams. Okay. I'm hoping I'll copy this over. Go. Right, that says given the functions at the top there. I do apologize. I just cut off my own writing, but we've been given the functions 2y plus x minus 12 equals 0 and xy equals 2. Yeah. PQ is parallel to the y-axis. Determine the maximum length of PQ, a vertical distance between A and B. Right. Couple things. First things first is whenever you are given equations of functions, they should always be in standard form. Neither of these are in standard form, so we will have to get them in standard form. I'll tell you why we need them in standard form in a second. Next thing, anytime you're told that a line is parallel to one of your axes, it means you are working with a vertical or a horizontal line. Because this line is parallel to your y-axis, which is a vertical line, it means that PQ itself is a vertical line. Okay, so that means it is perpendicular to your x-axis. The next little bit that we need to bear in mind is that we are asked for the maximum length of PQ. So anytime you see maximum, minimum, first derivative equals 0, blah, blah, blah. But what this means is this line PQ is not static. We can move it. PQ can be anywhere between these points of A and B. We just want to find at which x value it should line up with so that the distance between those two graphs is the maximum. Obviously, if you move it closer to B, the distance gets smaller and smaller. If you move it closer to A, the distance gets smaller and smaller. We want to know where it's a maximum. Okay, so all of that is important. Again, all we've just done is a bit of an analysis of our information. So first things first, we do need to get our equations in standard form, but let's discuss why we need them in standard form. So a little, again, tangential piece of information that is useful to us is to remember the following. So whenever you're looking at vertical distances, particularly between graphs, the way we find that distance is to take our top graph minus our bottom graph. Now, when I say graph, I mean the equation. The equation represents the y values. Now, this makes sense. If let's say, for example, on the same set of graphs, which is not that, so this, and we were looking for this distance PQ. If this y value was 5 and this y value was 1, that distance is 4. 5 minus 1, 4 units. So it makes sense that we're working with the y values because it is a change in y for vertical distances. And we always take the top minus the bottom. Obviously, you could just go ahead and count it, but the expression or the equation that we use is top graph minus bottom graph. So this is really important to remember. You kind of did do it in grade 10, grade 11 when you did functions. That was just really bad. But now we can apply the same set of knowledge to calculus. Okay. First things first, though, like I say, if we want to go subtract top graph and bottom graph, we need the y values. So we need to isolate y in both of these equations. So if we have a look at the straight, or at the first one, we were given, sorry, I don't know what's happening. Let's just go here. 2y plus x, I will move it up now, minus 12 is equal to 0. So I'm isolating y. 2y is equal to negative x plus 12. Divide both sides by 2. Y is equal to negative a half x plus 6. Now, we should be able to identify the fact that that is a straight line graph. So that's the linear functions equation. The other one I was given was xy equals 2. I want to isolate y, so y is equal to 2 over x. Again, we should be able to identify that that is a hyperbola. And so what we've been given here is one arm of a hyperbola. Those are my two functions. Now we go to this whole vertical distance situation and we decide, okay, which graph is on top? So who can tell me which function or which graph here is on top in between the points A and B? Which graph is on top? Lorato?
Ma'am, would it be the straight line graph?
Nice. Okay, good. So guys, we can see that our straight line graph's y values are greater than that of the hyperbola, so it is on top. And so that means we are going to take the straight line minus the hyperbola. So the straight line was minus a half x plus 6. We'll get there eventually. So minus a half. Cool. It's clearly side. Plus 6 minus my hyperbola, which is 2 over x. Oh, alrighty. So now we can get that expression. Absolute chaos. Negative a half x plus 6 minus 2 over x. So that is my distance for PQ. We want the maximum length, so now I have to find the derivative. But I first need to get my format correct. So negative a half x plus 6 minus 2x to the negative 1. Bring that x out of the denominator. And now we can find the derivative of PQ in terms of x. So this would be negative a half, the 6 falls away, plus 2x to the negative 2, because we subtract 1 from our exponent. And remember, it's now the first derivative equal to 0. Excuse me. So 0 is equal to negative a half plus 2x to the negative 2. And like I say, once you've made it equal to 0, get rid of that negative exponent. So a half is equal to 2 over x squared. We're going to times both sides by x squared. So x squared over 2 is equal to 2. Multiply both sides by 2. Obviously, if you can do this faster, that's absolutely fine. X squared is equal to 4. And once again, we're going to square root. So that means we get x is equal to plus or minus 2. Now, this kind of makes sense. If you go the other way, if you sort of extend further to negative infinity on the left-hand side of your graph, at some point you probably will get a maximum distance. I mean, you will definitely get a maximum distance between your graphs. Obviously, there's an asymptote to contend with, but there you go. However, if you look at your graph that you've been given, you have only been given information about your graph in the first quadrant. That is where x is positive. So we are working with where x is equal to positive 2. Now, the question did not ask, determine the value for x for which PQ will be a maximum length. It just said, determine the maximum length. We now know at what x value, so we now know that on this x-axis at 2, I will find the maximum length of PQ. But now I actually want to know what is that maximum length. We need to substitute back into our PQ expression. So PQ was equal to negative a half x plus 6 minus 2 over x, this original expression that we got, and we substitute into negative a half, that doesn't look like a half, negative a half times 2 plus 6 minus 2 over 2. And that gives you negative 1 plus 6, which is 5, minus 1, which is 4. So the maximum length between straight line and hyperbola for those specific equations we've been given is that where x is equal to 2 and produces a maximum length of 4 units. Hey, look at that. It actually ended up being exactly what I said earlier. Who knew? All right, so this is one, like I say, we can ask. It's actually something that, again, you have dealt with before because we do actually ask you vertical distances from grade 10, grade 11 already. It's not something that we test you a lot on, but it is something that we do start to ask from that point. And so we now have a method that uses calculus and derivatives in order to find maximum lengths. All right, I'm going to leave it up for you to screenshot. I'm aware of the fact that it's 7 o'clock. So if you need to go, you are welcome to go. Remember, last quiz of calculus, you've got one more quiz next week, and then obviously it's revision, so no more quizzes. So please, please do the quiz. Please, please, please. If you got questions, obviously I will say a bit an answer. So, Lorato, question?
Ma'am, I just wanted to ask, when we're giving the final answer, do we put it as like a coordinate, or can we just leave it as just 4 as the final answer?
So in this specific question, because it asked for a length, you would just leave it as 4. It's 4 units. You could say units if you wanted to.
Okay,
If
ma'am.
it just asked you for the value of x, you can just stop at x equals. I can't think of an example where it would ask you for a full coordinate because you're working out a length or you're working out an area or something like that. The coordinates more come in with the graphs where you find the first derivative to get your turning points and then you substitute back in to get y. Then you would write a coordinate. But in this case, a coordinate isn't necessary or applicable.